Well, welcome to the Stats for the Masses webinar. This is Adventures in Probability. This is the part one for the fundamentals. So this is the first of a four-part series, which I'm going to be presenting over the next couple of months. And it's been a long time coming, but it's finally here. Boy, it's just been a crazy, strange year. So hopefully getting back on track, which is great. So my name is Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. So thank you to all of those of you who took today to join us live here. Today I'm going to present a quick review of the history and basics of probability theory. That's where we'll get started. It's just an overview, like most of these webinars are, and much of it may seem simple. Today's not going to be so hard. As we get into it in the other sessions, it'll get a little bit more convoluted, but I hope the information you receive today is going to give you some ideas and guidance on how and why probability exists and how you can use it in your life and work. And as I say in all of our webinars, use what you learned today and apply it in a holistic way. Look at that big picture. As you'll see in this webinar, probability is very much about looking at the big picture. Okay, so let's go ahead and get started here and go to the next screen. Okay, come on. There we go. All right, so for those of you who come to the webinars often, you see the screen just about every time. But for people who are new, I like to go through what I do and tell you a little bit about me and Omega Statistics. It's a private practice consultancy, and I'm based in Southern California. I do medical and clinical research, all the clinical trial phases 1 through 4. I do design and analysis of experiments, epidemiology, large data, actually working on a COVID study or two right now, which is very exciting. I do help with dissertations. Typically methods and results chapters are my best ones to work on, but I do help with all chapters. Survey design and seminars, webinars. I can do off the rack or custom made. I just did a lovely webinar for a company up north in Seattle, and it turned out really well. In fact, I'm going to go ahead and make that available as a paid webinar on post-marketing clinical follow-up. So for all of you that are interested in clinical trials and such, that would be nice. Projects of any size. So I help individual researchers, small businesses, large corporations, government, and my motto is to provide elegant solutions effectively applied. So our task today is going to be to learn some history and fundamentals of probability theory. Okay, so I'm going to go through some history and background. I always find it fascinating where things come from and who's been involved in it. Actually, you would think maybe statistics might have a boring background or history. In the case of today, it's not all that exciting, but sometimes it gets, it's like a soap opera, some of the things that go on or have gone on in the past. And I have some stories. So I always like to look at the history and background. We'll look at the rules of probability. We'll look at the 3 axioms today. There's actually more rules that we'll go through in the next presentations, but we're just going to do some basics today. We'll look at set notation. That'll probably take you right back to junior high, but it's a good refresher. We'll define our events A or B and or B. Difference between independent and mutually exclusive events. So I'll show you kind of a nice way to be able to look at that, because people get that confused quite a bit. So first, let's go ahead and look at the theory or the history of probability. Actually, probability and statistics came from probability. So actually, you can say statistics and probability came from gambling. People were really big on gambling, especially back in the 1600s or so. And it's usually rich people betting on the ponies or maybe on dice games or card games. And they would meet with a probabilist, or they didn't call them statisticians then because they weren't around yet, but they would meet maybe in the back of a bar or something and get the odds and work it all out so they'd know how to do their bets. Well, there was the Chevalier de Mere problem, or it's also called the problem of the dice, but he was a gambler and he kind of set his own odds up, and he had been winning quite a bit. He was consistently winning by betting even money that a 6 would come up at least once in 4 rolls with a single die. Okay. However, whenever he changed it around a bit and played this other game, when he bet even money that a double 6 would come up at least once in 24 rolls, he was losing. And to him, and this didn't make sense. So I put a little graphic here so that I can define some of this nomenclature for you. Odds are used to determine the amounts paid out on winning bets. So this is why they are often referred to as as the price of a wager. Okay, a wager can have a price that's either odds on or odds against. Okay, odds on would be on down here. It's the potential amount you can win, but it'll be less than the amount that you put up. Okay, so odds against is the potential amount you can win, and it's actually going to be greater than the amount that you put up as a bet. So you're actually going to win your bet back plus more than what you bet. Even money, basically you double your money. Okay, and odds can be even money, and that's it's going to return exactly the amount that you wagered. Okay, so basically you're doubling it. So you'll still make a profit from winning an odds-on bet because your initial stake is returned too, but you have to risk an amount that's higher than you stand to gain. So big favorites are often odds on. Okay, because they're more likely to win. And when wagers are more likely to lose than win, like you have that horse is not going to win the race, or he hasn't done very well, you're going to have the odds against. And then, but you get a lot of rewards if the odds are like 25 to 1. You're getting for every dollar, you're getting 25 back. It's awesome, but harder to win. And trust me, people check this out and they're going to make sure they win a little bit more. And we're going to look on the fourth webinar. We'll look at casino games, game theory, and how to play them and what's the best game, and how they're set up. But I promise you, the casinos and anybody that's letting you do a bet is going to make sure that the odds are always in their favor, even if it's just a little bit. Okay, and that's typically how it is. You might have a 49% chance of winning, but the casino has a 51% chance, and that 2-point difference makes them millions. So he was desperately seeking to reveal the reason that he's failing in this 2-dice game. So he contacted his friend, who's a French mathematician, also a physicist. Usually people back then were many things. Blaise Pascal. And after careful analysis, Pascal found out what the problem was, and he got the right solution. It just needed to be seen from a different angle, from a larger perspective, actually. Here's how the Chevalier de Mere was looking at it, and it kind of makes sense. And that's the thing about probabilities. You think intuitively you're going to understand something and it's going to come out to be a certain number, but when you work with the probability and do it the correct way, sometimes you get these answers where you can hardly believe them, because they're just not intuitive like many things in life can be. But so the first game he played was with a single dice. So he, bet that he would roll one dice 4 times, and what was the probability he'd get at least 1/6. So the way he figured it out was he figured that it's 1/6 of a chance of winning every time times 4 plays. So he should be winning 2/3 of the time. Okay, so that's great. It's good odds for him. And in the second game, he kind of did it the same way. He says, well, if he managed to roll 2 6s in 20, like a pair of 6s in 24 consequent rolls, he knew again that the probability to roll 2 6s in a single roll was 1 out of 36, because you have 2 dice and each have 6 chances, right? So one possibility out of 6 times for 6 events. So he presumed that his chance to win, he did the same kind of calculations. He took that 1 out of 36 chance to win, multiplied it by the 24 games, and again, he got 2/3. So it was equal in his mind to the single dice game. He had the same outcome of 2/3. He should be winning 2/3 of the time, but it wasn't happening that way. So and that's the way you would think. You'd say, well, here's my chances of winning. Here's how many games I'm playing here. And so here I get it. The essence of the correct solution, which is this, is it consists in an indirect calculation of favorable events that are based on the calculation of losing events towards all the possibilities. So remember how I was saying you need to look at the big picture with probabilities. You can't just look at your chances of winning. You also have to take in consideration the chances of not winning and all the chances. What's the probability? You have to look at the whole picture, just not your chances of winning. So the house edge of all casino games is going to be evaluated on the same principle. And it's called the principle, it's an expected value. And another way to say it is long-term odds. When we'll discuss that more in a later session. But let's see how Pascal thought of the problem here. The first game was played with that single dice. Okay, so he said the probability to win would be 1 minus the odds of not winning, and then to the 4th power. So he did it this way, and he came up with 0.5177, which is over 50% chance of winning, right? So over long term, you're going to win more than you're going to lose. You're going to come out ahead because you're over 50% here. But on the second game, when 2 dice were rolled, again, he had the probability of winning would be 1 minus this probability of not winning to the 24th power. And look, it's less than 50%. So actually, over time, you would lose your money. And you can see you're taking into account the whole picture here. You're not just looking at actually the odds of winning. You're taking the odds of losing and subtracting it from everything, which leaves you with your odds of winning. So you have to take into account what the winning and the losing. And one, we'll talk about this concept of why we're subtracting it from one in a later slide here. So more history. We have probability. Started out as gambling. Probability is related to games of chance, and then it kind of moved into scientific and practical problems, and now it's come to what we have today in measurement theory and statistics. So this problem that the mayor had led to an exchange of letters between Pascal and Fermat, in which the fundamental principles of probability theory were formulated for the first time. So although a few special problems on games of chance had been solved by some Italian mathematicians back in the 15th and 16th centuries, there was no general theory that was developed before Pascal and Fermat started talking. And then later on came a Dutch scientist, Huygens. I might have said his name wrong, but he was a teacher of Leibniz, actually. And he learned of this correspondence between Fermat and Pascal. And shortly after, he published the first book on probability. And it's this one right here. And translated, it means the value of all chances in games of fortune. Okay, so he published that in 1657. But because of the inherent appeal of games of chance, probability theory soon became quite popular, and the subject developed rapidly during the 18th century. The major contributors during this period were Bernoulli and de Moivre. Okay, and Bernoulli, actually, you'll hear about him quite a bit in statistics. He did a lot of contributions to statistics. In 1812, Pierre de Laplace introduced a host of new ideas and mathematical techniques in his book. Okay, and translated to the analytic theory of probability. Okay, before Laplace, their probability theory was solely concerned with developing a mathematical analysis of games of chance. But he took this information and he applied it to many scientific and practical problems. The theory of errors, actuarial mathematics, statistical mechanics are examples of some of the important applications of probability theory that he developed and that was further developed in the 1800s. Like other branches of mathematics, the development of probability theory has been stimulated by the variety of its applications, right? Conversely, each advance in the theory has enlarged the scope of its influence. So mathematical statistics is one important branch of applied probability. Other applications occur in widely different fields like genetics, psychology, economics, engineering. Many workers have contributed to the theory, since the time of Laplace. Among the most important are Chebyshev, Markov, von Mises, Kolmogorov, a lot of big names in statistics there. One of the difficulties in developing a mathematical theory of probability has been to arrive at a definition of probability that is precise enough for use in mathematics, but still comprehensive enough to be applicable to a wide range of phenomena. So the search for a widely acceptable definition took nearly 3 centuries, and there was much controversy and a lot of arguing between large minds. The matter is finally resolved in the 20th century by Kolmogorov, a Russian mathematician, and he outlined an axiomatic approach that forms the basis of the modern theory. And since then, ideas have been refined somewhat, and probability is now part of a more general discipline known as measure theory. Okay, so we really have Kolmogorov to thank for the axiomatic approach. And here they are. Here's the 3 axioms that he came up with. The first axiom states that the probability of an event must be between 0 and 1, where 0 represents an event that'll never happen, and 1 represents an event that will definitely happen. Okay, so everything, so we all work, statisticians and people in probability work between 0 and 1. Drives mathematicians nuts, but that's where we live. We live within 0 and 1. Second axiom is the probabilities of all events on the sample space or the event space always sum up to 1. So basically something must happen, right? And all the things that are happening in your whole sample space, all your events, the probabilities need to add up to 1 to make everything included, okay? The third axiom is in the case E and F, these are like events that are mutually exclusive, also called disjoint, and we'll go through that in a little bit. Then this following equation is going to be valid, okay? Because when they're mutually exclusive, it means they're not sharing any information between the events. So basically what you can say is the union of these two events is equal to just adding them together, okay? And from this third axiom, you can also show that this null set, where nothing's inside the set, is going to equal 0. I could kind of show that, but it's kind of hard to draw. Let's say that we have like the probability. Oh, let me see if I get the little, I'm going to try to write here. Okay. So we have the probability. Okay. And we'll have event E with the union of a null set. Okay. Knowing from that, if we're saying these are mutually exclusive, okay, then we could use this here. It's going to equal the probability of E plus the probability of the null set. Okay, well, this is would be the same as saying the probability of the null set is going to equal 0. Okay, so that's how you can kind of come up to that. Okay, this is the very basic probability information, but it'll be enough for today's examples. This website link down here at the bottom of the slide is for StatTrek, and it's an easy read. Okay, and as I've said, if you know me, you know this is one of my sayings. In statistics, we don't know the truth, so we have to make a guess at it. Statisticians are really good guessers. Every event, person, etc., we measure is different, so we have noise, right? So to make our good guess, we need to know how probable or likely an event is to occur in a given situation, okay? So the probability is the chance that something's going to happen, okay? So let's go ahead and look at a little bit more of the definitions here. So before discussing these rules of probability, let's go ahead and look at some of these definitions. So an event means one or more outcomes, okay? Think of one outcome as getting heads on a toss of a coin. More than one outcome, think of rolling an even number on a die. So then, you know, you could have a 2, 4, or 6, right? There are events. Rolling a die and getting an even number, that's an event, but you have 3 outcomes. If you want to get ahead on a coin toss, you only have one possible outcome, and that would be the heads, right? 2 events are mutually exclusive or disjoint if they cannot occur at the same time. For example, I can't turn both left and right at the traffic light. I can only do one or the other. So it's always going to be, you can't turn both ways. You can only turn one way. Those would be disjoint or mutually exclusive events, okay? Conditional probability is the probability that event A occurs given that event B has occurred. Okay, that's called a conditional. So the conditional probability of event A given B is usually noted by this. You'll see this a little bit today. You'll say probability of event A given B. You'll have the straight line down there. And that straight line either means such that or given. So A given B. I always like to think of it as B given A because I always think A should happen before B. But again, it is what it is, right? You can call the events whatever you want. Just make sure you remember what you called what, right? So the complement of an event is the event not occurring. The probability that A will not occur, then you probably have, say, something about, you have the probability and you'll put of A, and you'll put like this little asterisk up here. Another way you might see it is A complement. And so it'll have a little C up here. Okay. So those are either for those are for complements. Okay. Intersections, the probability that events A and B both occur is the probability of the intersection of A and B. So you'll see it like this. Probability A intersection, so it's an upside down kind of U, B, okay? And that means they both have to occur. This would be right in here. So you have some elements in here of A, like say you have some things here, and some elements in B. And this is a Venn diagram. We'll look at those next in part 2. So these three things in here are shared by both A and B, and this would be your intersection. The probability that events A or B occurs, the probability of the union of A and B. This would be everything in A and everything in B. Okay, and then you would need to subtract out the parts that are shared. And I think we look at that maybe a little bit later today, but it would be everything all together. The reason you're subtracting out this little intersection when you do the union is because you don't want to count twice. These guys would be counted twice otherwise, and we don't want to do that. Okay, and the probability for union is going to be written like this. This is where you see the U. And these get kind of confusing when you think about, well, what union or intersection, you know, and then it's like, okay, union means everything, okay? Intersection means what's shared. Sometimes you'll see people when they talk about the union, they'll say it's the probability that events A or B or both happen. So they'll add that or both. But if you hear somebody say A and B, they're talking about intersection. They say A or B or both, then they're saying union, okay? So dependent and independent, basically, if the occurrence of event A changes the probability of event B, then the events A and B are dependent, okay? On the other hand, if the occurrence of event A doesn't change the probability of event B, then events A and B are independent, okay? And so we'll look at an example of that in a little bit. Some more terminology. Here's a cute representation of the first definition on that previous slide about mutually exclusive. Two events are mutually exclusive or disjoint. There's two different names for it if they cannot occur at the same time. So I did get this slide from this place down here. You can read a little bit more about Venn diagrams, but it's actually two events. Okay, people who understand Venn diagrams and people who don't understand Venn diagrams. You can't do both, right? It's like you can't turn left and right. So you either understand or don't. There might be some people that kind of understand, but they're not in here, right? We're just looking at people who don't and people who do, and never the two will come together. Okay, so they will stay separate. Okay, let's revisit those three rules again. Probabilities cannot be negative. They have to be between 0 and 1. You can't have a negative 50% that something's going to happen or not. Okay. All probabilities in the same sample space must add up to 1. So that's the collection of all possible outcomes for all events must add up to 1. Actually, this is the reason I named omega statistics omega statistics, is because omega in statistics is all possibilities. Okay, so sample space or the population of all possibilities. So that would be your sample space basically. And so I kind of like that. And I said, oh, I'll call it omega. So, and the third one, the probability of an event and the complement of the event must add up to 1. That's the complement rule. So you have the probability of an event happening and the probability of an event not happening. That will add up to 1 because that covers your whole sample space. Okay. And these are also rules of logic. And there's also some mathematical rules of probability. We'll go through them in a later event, but if you want to read and get a start on it and get some understanding, you can go here, and there's some very good information on the mathematical elements of probability. Okay, so here's a nice little picture. Probability is the chance that something's going to happen, okay, and it can be shown on this line, okay. Probability in an event occurring is somewhere between impossible, down here, which would be 0, and certain, which would be your 1. Right, as well as words, we can use numbers to show the probability of something happening. Impossible, 0, certain is 1. Different probabilities are going to lie between the 0 and between the 1. Okay, the higher the probability, the more likely you're going to observe the event or outcome. So it's kind of unlikely. You have a 1 in 6 chance of getting the number you want on a dice. Say you want a 3. Okay, so you still have a 1 in 6 chance of getting that. Not very probable. Okay, even chance is 50-50. So you're just as equally likely to see it as not see it, okay? And then you have a 4 in 5 chance of getting a green ball here, okay? Out of the 5 balls, 4 are green. So that's pretty highly likely, right? 20, 40, 60, yeah, you're 80% probability there. And then of course your certains here. Okay. So you can forget everything you know about numbers. In fact, you don't even need to know what a number is, because this is where probability starts. Instead of math with numbers, of course, we're going to use numbers quite a bit. I want you to start thinking about probability as things. It's a collection, a set of objects. Okay. The objects in a set are called the elements of the set. Okay. Let me go ahead and erase that drawing there. Okay. And a well-defined set is a set in which we know for sure if an element belongs to that set. Okay. Example of sets versus not a set. A set would be maybe the set of all years I've been alive. Okay. So that's the years from 1963 to now. Okay. It could be a set of all the dogs I've ever owned. That's well defined. Okay. Not a set would be the set of best guitar solos of all time. That's not well defined because it's a matter of opinion. My idea of best guitar solos might have a different number of them in there, and there might be totally different solos than yours, right? So that would not be a set. Okay, so you have to exactly know what's in that set, and it has to be, everything needs to be able to define, because why? We're going to assign probabilities to things in that set. Okay, so now we have some set notation. Okay, when talking about a set, we usually denote the set with a capital letter. Okay, roster notation is the method of describing a set by listing. So you just make a big list. Okay, so in this case, let me get my little spotlight here. Let A equal the set of all the dogs I've ever owned. Okay, so I had Rex, and then I had another Rex, and my parents like to name dogs Rex. So Rex 1 and Rex 2. Okay. Then I had Herbie, Goat, Spencer. Now we have Cheeto. Cheeto's great. So that's all listed out, and it's in roster notation. Okay. Let set B equal the set of odd numbers greater than 0 and less than 10. So in roster notation, we would just list them like this, put them inside our little brackets, mid to commas. Okay. So it's all listed out. Sometimes we can't list all the elements of a set. So, for instance, the number of years I've been alive, well, that's a lot of elements. 57. I just turned 57. So anyway, that'd be a lot to write out, right? For instance, we have Z here as a set of integer numbers. Okay, we can't write out all the integers, or infinitely many integers, so we adopt the convention using dots. Dot, 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 3 dots. The dots mean continue on in this pattern forever and ever. So here we go, set of integer numbers. We go dot, 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 so it's from negative infinity. And we show a couple examples here just to get a good idea of what we're doing, right? And then some more dots after, and that's going to go all the way up to infinity, okay? You might even, sometimes you might even see the infinities in here before, like a negative infinity here and then an infinity there before and after the dots, but this works just fine, okay? And then here, W represents the set of whole numbers. So again, we start at 0. You don't have negatives, right? So we're starting at 0 and we're going up to infinity with the dot, dot, dot. Okay, then there's set builder notation. Okay, when it's not convenient to list all the elements, we'll use a notation that employs the rules in which an element is a member of the set. It's called set builder. Basically, we could say here's some examples. Set V is our names of people, given that they're citizens registered to vote in Riverside County. So really what we're wanting are the names of the people who are registered to vote in Riverside County. But we didn't list all the names, but it's an understanding that it'll be those people. Okay, here's event A. It's going to be the X such that X is greater than 5. So this is the set A that has all real numbers greater than 5. Okay, and the symbol, this long symbol, is read such that or given. A lot of times you'll hear people say given. Okay, and so that's how and we use set builder notation quite a bit, especially when we start doing conditional probabilities and computations. So we have special sets. Try not to use any of these letters because they're already taken. Okay, we have the set of all natural numbers will be N. Set of whole numbers will be W. Okay, set of integers will be Z. Q is the set of rational numbers. Okay, it'd be X such that X equals P divided by Q, where P and Q are elements of Z, and Q is not equal to 0 because you can't divide anything by 0. It's undefined. Okay, so that's a set of rational numbers. H would be the set of irrational numbers. An irrational number, if you can't remember, it's a real number that can't be made by dividing the two integers. You can't divide. Okay, irrational means no ratio. basically. So it is an irrational number. We aren't saying it's being difficult or it's being irrational or it's, you're just being irrational. It just means you can't make a ratio out of it. Its decimal is going to go on forever without repeating. So think of things like pi, things like that. Set of real numbers is R, okay? And the set of complex numbers is C. You probably remember this from a long time ago, but a complex number, it'll be A plus B I. It's got this imaginary number, I. So you have a complex number, okay? And because you have this imaginary element of it, it satisfies this equation. I squared is -1. And you probably remember back in high school having to deal with this. Because no real number will satisfy this equation, I is going to be the imaginary number, and that's going to make this a complex number. Okay, so those are all the different special sets. There may be more, but those are the most popular ones. Okay, now we have universal sets and subsets. Universal set is denoted by U, universal, right? And it's a set of all possible elements used in a problem, okay? When every element of one set is also an element of another set, we say that the first set is a subset. So it's a small group that comes out of the universal set, or maybe in a set of the universal set, but it's anything that has those elements of another set was going to be a subset. So an example here would be A is our one set there, 1, 2, 3, 4, 5. Okay, and B has the numbers 2 and 3. So we can say B is a subset of A, and the notation we use is this: the set B subset of A. Okay, have this little line under it. Okay, here's another example. If we have S as 1, 2, and 3, we want to list all the subsets of S. Okay, some things to remember: that S is going to be a subset of itself. We're also going to have that null set in there, okay, always included as a subset, okay? And then, of course, we'll have just these individual numbers, 1, 2, 1, 3, 2, 3, and then, of course, 1, 2, 3. So basically, 1, 2, 3 is going to be the same as S, okay? Just kind of written differently, okay? Okay, proper subsets as opposed to improper. I don't think there's really improper, but there's proper subsets. A would be a proper subset of B if and only if every element A is also in B, and there exists at least one element in B that is not in A. Okay, so if we look at the definition of subsets and let our minds wander a bit, we come to a weird conclusion, right? Let A be a set. Is every element of A in A? Well, yes, of course, right? Every element of A is going to be in A. So that means that A is a subset of A. It's a subset of itself. But this doesn't seem very proper, does it? If we want our subsets to be proper, we introduce the proper subsets, okay? The little piece here at the end of the statement, at least one element in B that is not in A, it's there to make sure that A is not a proper subset of itself. We say that B must have at least one extra element. So here's some examples. 1, 2, 3 is a subset of 1, 2, 3, but it's not a proper subset of 1, 2, 3. It is basically the subset. It's the same set, but it's also a set has its own subset. 1, 2, 3 is a proper subset of 1, 2, 3, 4 because the element 4 is not in this set, in the subset, okay? So therefore it's proper, okay? When A is a proper subset of B, then it's also a subset of B, okay? So proper subset, you have subset and then you further define it as to whether it's proper or not. Always a subset though. Okay, more set notation. So when we say A is a subset of B, we're going to write it like this. When we say that A is not a subset of B, we're going to put a line through it, okay? And when we talk about proper subsets, we're going to take away this little line at the bottom, okay? And it's just going to become A is a proper subset of B, or if we want to say the opposite, A is not a proper subset of B. You're just going to take that little line away. And we'll play with this as we go through our little series. Then we have the null set or the empty set, okay? It contains no elements. Sometimes you'll just see it like this with nothing in it, with just the brackets, or sometimes you'll see it like this, okay? Empty set's always considered a subset of any set. So here's a 0 in there. And the question is that an empty set? And the answer is no, because there's an element in there of 0, right? So it's not empty. If it has to just be blank, okay? And that means empty, okay? This isn't empty. There's a 0 in there. Remember, don't think of them as numbers. Think of them as things, okay? Okay, so intersections. When an element of a set belongs to 2 or more sets, we say the sets will intersect, okay? So the intersection of a set A and B is denoted by that upside down U, okay? And you're going to hear terminology and, okay? And this is confusing because I always, for the longest time, if you're saying A and B, that seems to intuitively make you think that's everything in both sets, A and B. But actually it's A or B where you're thinking of everything. So when you have and in this context, that means that they have to be in both, the element has to be in both A and B, both, okay, for it to be an intersection. So here's an example. A has 1, 3, 5, 7, 9, and B has 1, 2, 3, 4, 5. So the A with the intersection of B would be 1, because they're in both, and 3's in both, and a 5's in both. And there you go. And that would be your intersection, okay? And like I said, you'll usually see and. And, a lot of things in probability I learned, you basically just have to keep telling yourself the same thing until it sinks in. I did do the same thing with some statistics things. Someday I'll tell you about how difficult it was for me to learn about null hypotheses and you're testing for nothing. That's a whole other thing we can talk about another time. Mutually exclusive sets. Think of mutually exclusive of 2 events that can't happen at the same time, okay? 2 sets A and B are mutually exclusive if the intersection between A and B is a null set, right? There's nothing there that they're sharing, okay? Here's an example. It rained today. And the set B is it did not rain today. Well, you can't have it raining and not raining, right? Just like the same thing. I turn a left turn or right turn, right? You can't do both. So therefore, you'll have that null set and you'll have that mutually exclusive, which is not independent. Mutually exclusive and disjoint are the same, but independent something else, and I'll show you in a minute. Okay. So the union now of 2 sets A and B is denoted by that U, okay? A union B. We want to say X, given that X is in A or X is in B. One can also say X is in A or B or both. Sometimes that helps you remember that that's the or is for everything for the union. So here's an example. Again, those same sets, 1, 3, 5, 7, 9, 1, 2, 3, 4, 5. So we want everything from both sets in there, okay? If elements are in both sets, don't repeat them. So for instance, 1 is in both, but I don't go 1, 1, right? I just put that 1 there one time, okay? It's represented in this set one time and this set one time. However, we don't want to put two 1s in because it'll mess up your probabilities, and we don't want to do that. And we will learn that in a later lecture. Complement. The complement of a set is denoted by putting this little apostrophe here or putting the C up there as a superscript. And a complement is X given that X is not in set A. So what it would be is, for an example, say that we have this, the U, right here is our universal set, right? 1, 2, 3, 4, 5. And then A is a subset. It has 1 and 2, okay, in there. Then the complement would be 3, 4, and 5. Okay, so in this example, U's would be that sample space or the larger set, all possible outcomes. We can also say that A is a subset of U, right? And then the A complement would be the things that aren't in A, that are still a part of U, okay? Cardinal numbers, is the number of elements in the set. And you have the little n, which means number, in set A. So if we let A equals 1, 3, 5, 7, 9, there's 5 elements. So n of A is 5. Okay. Cardinal number formula for the union of 2 sets. So if we have A union B, it's going to be the same as the number of elements. So the number of elements in both A and B, A or B or both, will be the number of elements in A plus a number of elements in B, and then we're going to need to subtract out that intersection because otherwise you're going to be counting them twice, like I told you on that earlier slide, okay? The cardinal number formula for the complement of a set is going to be the number of elements in A plus the number of elements not in A, right? A naught, and that's going to give us this your universal set, okay? So it's everything that's in A, everything that's not A, that's everything that's in that sample space or that universal set. So let's look at mutually exclusive and disjoint events. Two events A and B are said to be mutually exclusive if it is not possible that both of them can occur at the same time. And so we've looked at this quite a bit already today. So example, we're going to toss a coin. A is going to be the event that the coin lands on heads, and B is going to be the event that the coin lands on tails. Okay, so it follows that in a single coin toss, and the coin's fair, it's not rigged, right? Events A and B are mutually exclusive. Mutual exclusivity can be shown on a Venn diagram, tails and heads. There's our two events in our spaces, you know, so mutually exclusive, okay? Here's another one. Here's our sample space. It's an epsilon up here, okay? So it includes both these sets inside a universal set. Actually, they're, you know, it's possible you might have some things out here. They're just not being included in our events here, right? They're just outside of, out of our events here, okay? So we have odd numbers here, and then we have even numbers here. Well, they're never going to share. Okay. And then here again, S is our sample space. And like I said, it could be possible to have some things out here, but we're going to make it easy today. We'll look more at this later on. But A and B, there's just, in general, whatever's in A is not in B. Okay. And so basically, and you see something like this, where they're apart like that, that's mutually exclusive. There's no intersection. Okay. Now, independence. Events A and B are said to be independent if the probability of B occurring is unaffected by the occurrence of the event A happening. Okay, so, you know, sometimes you read that and you go, what? Okay, so we'll do an example. We're going to toss a coin, but this time we're tossing it twice. Okay, we're going to let A be the event that the first coin toss lands on heads. Okay, in addition, we're going to let B be the event that the second coin toss lands on heads. Okay, so clearly the result of the first coin toss does not affect the result of the second coin toss. So it follows that the events A and B are independent. Okay, and a lot of times you can see these kind of things easier on a tree diagram. So here's our first coin toss. We have 50% that we can get heads, 50% that we can get tails, right? Half the time we'll get heads, half the time with a fair coin we'll get tails. Okay, so that's our first toss. So maybe we got heads on our first toss. So we're gonna toss it again. Same probabilities for heads or tails, didn't change anything, right? Same thing, even if we got tails on our first toss, when we go to toss it again, we're going to have the same probabilities on getting a heads or tails. So this is a nice way to see it. If you see things like this and the probabilities don't change, then that means you have some independence there, okay? Now, this is not independence. This is conditional probability. Okay, and I borrowed it from this place, and you can read a little bit more about conditional probability. It's about like if you're able to construct tree diagrams, you know, what are your odds or your chances or probabilities of passing the class? Okay, if you're able to construct tree diagrams, okay, in the class it looks like maybe 78% were able to. There's a probability of 22% that we're not able to, okay? So we go here, now are they going to pass or fail? It does matter. These outcomes here, you have 0.78. Well, now if you pass, if you know how to do a tree diagram, well, then you probably have a 97% chance of passing the class, okay? But if you don't know how to do your tree diagram, then you go down to 50%, 57% of passing the class, okay? And then here's your eventual passing of the class, depending on what kind of person you are, right? You know, so usually with the tree diagrams here, oh boy, you know, if you know your tree diagrams, your odds are going to be pretty good about passing the class, okay? Very few will know tree diagrams and fail, only 2%, right? But as you can see, these things change depending on what your first answer was. Then your pass and fail are different, whether you are knowing your tree diagrams or not. Okay, so that's a good way of seeing conditional probability or events that are not independent. Oh, already up to the references. I guess we covered it in about an hour today. I haven't really seen any questions coming in, but here's some references to learn more. Common symbols used in set theory, definitely look that up and take a look at those. Here's a link from LibreText on types of probability, which is very interesting to look at, and a tutorial on probability from Lisa Sullivan from Boston University School of Public Health. A very, very, very informative, and it's rather large. So if you really want to start getting into things and reading more about them, I would probably start there. Okay, and let's see what else we have. Oh, yes, keep in touch. Sign up for the email list. If you get on my email list, and I try to every week. I've had some health issues lately, like over this year, but I'm getting better and better all the time. But I try to do a weekly stats grab bag, and it kind of tells you what's going on, what's coming up, events that are coming up, as far as webinars and some, paid events or new offerings. Also, I like to kind of discuss some things that have happened during the week, statistically speaking, that might be useful to you. So it's always nice to get that information. And our next webinar actually is to be announced, but I think our next webinar is going to be October 14th is part 2. And we're going to look at probability in pictures. Okay, so we got a little bit of the pictures looked at today, but next month we're really going to get into the nitty-gritty of probabilities, and we're going to start with pictures because pictures are nice and they show so much. And yes, and I will send the slides, and I will send a recording, and I'll send a link. So if you want to sign up for those other 3 probability webinars, if you have questions, you can always email me too. Okay, I'm always happy to answer. If it's a simple answer or I can send you a reference, I love to do that. You take your time out to come and visit me. I would love to help you out. Okay, so I think that is it. Okay, well, thank you everybody for coming, and have a great rest of the day and great rest of the week. And yes, I'll see you hopefully in a couple weeks. Okay, thanks a lot. Bye-bye.